Optimus can see you now. The patent behind Tesla Optimus eye structure has just been revealed. This remarkable development recently appeared on X, highlighting what could be a major technological shift for Tesla. A newly approved Tesla patent, granted on May 26, 2026, raises a fundamental question for the future of robotics. How can a humanoid robot move safely through the unpredictable physical world when its computer vision is constantly exposed to dust, grease, rain, and wind? Tesla's answer appears to be inspired directly by nature. While the robot's AI brain is designed to imitate human intelligence, its physical vision hardware also needs something similar to blinking and tearing in order to protect itself. Titled simply Lens Cleaning System, the newly published patent describes an advanced integrated hardware architecture that could represent an important step forward in autonomous design. By combining software-based debris detection, microscopic fluid delivery, and an active mechanical wiper, Tesla has created a biomimetic camera housing that closely imitates key functions of the human eye. Instead of depending on large external cleaning systems or conventional high-pressure spray nozzles that could interfere with the robot's appearance, this compact spherical lens assembly can automatically identify visual obstructions and activate localized fluid cleaning and structural eyelids to preserve optical clarity. This development provides a hardware-level answer to one of the biggest challenges facing vision-dependent autonomy: the gradual loss of performance caused by real-world environmental conditions. Although the automotive community initially connected this technology with the cybercab robotaxi, the patent's compact, self-contained structure and highly biomimetic design strongly suggest another possible destination: the highly anticipated Tesla Optimus Gen 3. In humanoid robotics, vision-based neural networks depend completely on receiving clear and reliable visual information. Consider the engineering challenge. A camera mounted on a modern vehicle can sometimes use passive airflow or high-speed movement to help remove light rain, but a humanoid robot moving at a normal human walking speed of around 1.2 to 1.5 meters per second inside a factory, warehouse, or home does not have that benefit. At such low speeds, aerodynamic forces provide virtually no meaningful dirt removal. Under these conditions, even a tiny layer of airborne dust, machine oil, or other residue can significantly reduce image contrast, potentially severely affecting the edge detection neural networks responsible for understanding the environment. Earlier Optimus generations depended more heavily on passive protection and manual maintenance after extended operation. Integrating a self-cleaning eye assembly into the Optimus Gen 3 platform could therefore represent a major move toward continuous 24/7 operation without regular maintenance downtime. This miniature closed-loop system is designed to work through an intelligent and highly precise sequence that could fundamentally improve machine vision durability. First, the robot's onboard vision neural network identifies an immediate reduction in image contrast, localized pixel obstruction, or visual distortion created by outside debris. The system can then instruct internal microchannels to deliver extremely small quantities of specialized cleaning agents, potentially including water, alcohol-based solutions, or surfactants, directly onto the curved lens surface to loosen and break down contamination. At the same time, a tiny integrated mechanical wiper moves across the spherical surface, removing more stubborn particles such as dried dirt or insects before retracting into a concealed inactive position. The result is a restored and unobstructed field of view. This upgraded vision architecture could give Optimus Gen 3 the ability to perform demanding tasks in environments where vision-based robots previously struggled. In heavy industrial and manufacturing facilities, Optimus could potentially carry out precision welding, machining, and component assembly, while surrounded by airborne metal particles, oil mist, and sparks. These are environments where human visibility can deteriorate rapidly and conventional camera lenses may require frequent manual cleaning. For outdoor and hazardous applications, such as agricultural harvesting, search and rescue across muddy terrain, or chemical spill containment, the robot could potentially maintain reliable depth perception and highly accurate spatial mapping even after exposure to mud, chemicals, or heavy rainfall. In homes and commercial environments, the same self-cleaning capability could allow Optimus to handle messy household tasks, kitchen sanitation, or dusty warehouse inventory operations. That would help move the robot from a delicate laboratory-style prototype toward a more resilient autonomous machine capable of handling some of the dirtiest real-world jobs. And the improvements clearly don't end with the vision system. The latest V25 developments already appear highly advanced. While Optimus Gen 3 remains largely concealed from public view, if Tesla is already revealing technology at this level, the next generation could represent a completely different stage of development. The shift from a technology demonstration prototype toward a genuine industrial machine is especially visible in the mechanical upgrades incorporated into Optimus V25. Rather than concentrating primarily on smooth, cinematic movements intended for demonstrations, Tesla's engineers have extensively redesigned the biomechanical system around durability, thermal efficiency, and high-volume manufacturing requirements for demanding industrial environments. One of the most important changes involves moving the high-voltage battery pack from the chest and upper spine region downward into the pelvic structure. This change lowers the robot's overall center of gravity by several centimeters, reducing rotational inertia during bipedal movement and helping minimize continuous loads placed on the ankle and knee actuator assemblies. One visible benefit of this redistribution of mass is a substantial reduction in upper body sway, reportedly bringing torso movement down to an extremely small margin. This improves the stability of the head-mounted sensors and camera systems, allowing them to provide more consistent visual information to the robot's spatial processing neural networks. At the same time, the articulation system used in Optimus V25 has undergone a major redesign through the introduction of four-bar linkage mechanisms at important load-bearing areas, such as the hips and knees. This system allows nonlinear transmission of force while automatically changing the mechanical advantage according to the joint's angle of movement. The objective is to improve the efficiency of the robot's electric motors. When Optimus performs a demanding lifting motion, such as bending down to pick an object up from the floor, the four-bar linkage can extend the effective lever arm to reduce the peak electrical current demanded by the motor. During the forward swing portion of walking, the mechanism can instead prioritize angular velocity. This established mechanical engineering approach is described as a major factor behind potential reductions in total system energy consumption, helping structural components remain within more efficient temperature and operating ranges. Combined with the robot's battery system, this could potentially extend operation beyond a standard 8-hour shift without requiring complicated liquid cooling architecture. The robot's real-world movement capabilities are also represented by a sustained walking speed, designed to remain compatible with normal human movement patterns inside logistics corridors and automotive production facilities. This is important because a humanoid robot operating alongside people cannot create localized bottlenecks simply because it moves too slowly. To maintain precise movement while carrying different payloads, Tesla has implemented high-frequency joint-level torque control. The system continuously analyzes information from strain gauges and current sensors thousands of times per second, detecting extremely small deviations in movement. If a foot lands on an uneven section of concrete or suddenly slips across an oil-covered factory floor, the joint-level controller can immediately adjust mechanical stiffness and force output within milliseconds. Rather than waiting for a slower centralized computer command, the local control system can react almost instantly to preserve the robot's balance. Inside manufacturing and assembly environments at Fremont, these improvements in actuator performance and structural rigidity could allow Optimus V25 to perform difficult operations, such as removing sharp stamp metal components or heavy brake assemblies, weighing as much as 20 kilograms from deep storage containers. Such tasks require the robot to continuously shift its center of gravity while controlling finger-gripping forces through joint-level feedback. The system needs to apply enough torque to lift heavy parts, while avoiding deformation of softer components or damage to delicate wiring harnesses. When moving from industrial facilities into domestic environments, the combination of a lower center of gravity and high-frequency torque control can also become a safety mechanism. If the robot accidentally trips over toys, thick carpeting, or encounters a household pet, it can automatically adjust its posture and perform controlled recovery steps. The combination of potential energy savings and extremely sensitive tactile feedback could allow the machine to work independently without being tethered, performing delicate household tasks such as placing porcelain dishes into dishwasher racks, carrying heavy baskets filled with damp laundry, or cleaning sensitive furniture surfaces without causing damage. So why could AI-5 become one of the most important breakthroughs for Optimus Gen 3? Tesla is operating under intense pressure in the humanoid robotics race and appears to be behind some early-moving competitors when it comes to commercial deployment. At present, Tesla's Optimus fleet is described as consisting of only a few hundred internal prototypes, primarily focused on collecting data rather than delivering large-scale factory value. By comparison, Figure AI has reportedly operated Figure 2 continuously for 11 months at BMW Spartanburg, accumulating more than 1,250 hours of real-world operation and processing over 90,000 sheet metal components with reported accuracy of around 99%. Agility Robotics has surpassed 100,000 tote handling deployments with Digit at GXO Logistics in Georgia, and has also expanded into Toyota facilities in Canada. Perhaps most significantly, Chinese companies are reported to control a very large portion of the global commercial humanoid market. Agibot has reportedly shipped more than 5,100 units, while Unitree Robotics has delivered more than 5,500 robots and is working toward production levels of 10,000 to 20,000 units. Tesla, however, appears to be pursuing a different strategy. Instead of prioritizing the earliest possible pilot customers, Elon Musk is attempting to build an enormous manufacturing and scaling system. Tesla has even reportedly stopped Model S and Model X assembly operations at Fremont as the company restructures portions of the facility around a manufacturing ecosystem designed specifically for Optimus Gen 3. The planned production system is described as having an initial capacity of approximately 1 million robots annually. Combined with another facility at Giga Texas, the long-term objective could reach 10 million Gen 4 robots per year by the end of the decade. In other words, Tesla is attempting to bring the principles of high-volume automotive manufacturing into humanoid robotics. At the center of this strategy is Tesla's custom AI-5 silicon architecture. The chip has reportedly completed its tape-out stage, indicating that it is moving toward production through Samsung's Texas operations and TSMC's Arizona facilities. Most importantly, Elon Musk has indicated that AI-5 is being prioritized for Optimus Gen 3 ahead of electric vehicles and robotaxis. The AI-5 processor is described as delivering neural network inference performance comparable to a much more expensive NVIDIA-class GPU, while consuming only around 250 watts. This could significantly reduce the energy burden compared with high-end computing hardware. Tesla achieved this efficiency by removing components that are less important for the robot's specific workload, including traditional graphics pipelines and separate image processing hardware, allowing more of the silicon area to focus directly on neural network computation. This power efficiency is especially important because humanoid robots operate under strict battery limitations. Many platforms carry battery packs in the range of only 2 to 3 kilowatt-hours. If the onboard processor itself consumes more than 500 watts, as some powerful data center processors can, the robot's available energy for movement and physical work becomes severely restricted during a normal factory shift. AI-5 could address this limitation by providing Optimus Gen 3 with substantial local computing power without requiring constant dependence on Wi-Fi or cloud servers. This represents a significant departure from systems that rely on an image snapshot, cloud processing, and response cycle. Tesla instead appears to be moving toward an end-to-end neural architecture capable of processing continuous video in real time. This approach is similar in philosophy to the evolution of Tesla's FSD system, where large amounts of manually written logic were replaced by neural network-driven processing. Musk has also recently discussed a software architecture referred to as Digital Optimus. Instead of relying on isolated static images in the way some AI agent systems operate, the concept involves processing continuous video streams over several seconds to better imitate human perception. The approach parallels the transformation of FSD toward end-to-end neural networks. Critically, this processing is intended to run locally on hardware such as AI-4, rather than depending entirely on expensive cloud computing. That could make Optimus Gen 3 a genuinely real-time AI platform capable of continuously interpreting and adapting to its surroundings. Tesla's biggest potential competitive advantage, however, may be its data engine. A global fleet of more than 4 million vehicles has accumulated billions of miles of driving data across extreme weather conditions, complex intersections, and unpredictable real-world situations. This creates a proprietary visual dataset that competitors cannot easily reproduce. Tesla is also collecting video and operational information from workers at Fremont to help train Optimus in human-like manipulation. In addition, the company is developing methods that could allow the robot to learn skills by analyzing instructional videos available on the internet. This training process can be accelerated through virtual neural world simulations, where robots can practice tasks at speeds hundreds of times faster than real life, without exposing physical hardware to wear or damage. To support this enormous machine learning operation, Tesla has activated its Cortex-2 supercomputer at Giga Texas. The system is described as exceeding 130,000 equivalent GPUs and potentially drawing as much as 500 megawatts of power, an amount comparable to the electricity consumption of hundreds of thousands of homes. Combined with Cortex-1 and its more than 100,000 GPUs, Tesla could operate a combined computing fleet exceeding 230,000 GPUs dedicated to training systems such as FSD and Optimus. The amount of data entering this training pipeline is enormous, potentially equivalent to hundreds of years of continuous driving information every day. That creates a proprietary technological asset that even extremely wealthy technology companies would struggle to reproduce quickly. As more Optimus robots are deployed, those machines can collect additional real-world data, send unusual edge cases back to centralized computing systems, receive improved software through over-the-air updates, and continuously contribute to the next generation of models. If Tesla successfully scales production at Fremont during the 2027 to 2028 period, Optimus Gen 3 could push humanoid robotics into an entirely new phase. A globally distributed, continuously learning, and increasingly self-improving AI network. If Tesla successfully scales production at Fremont during the 2027 to 2028 period, Optimus Gen 3 could push humanoid robotics into an entirely new phase. A globally distributed, continuously learning, and increasingly self-improving AI network. And if Tesla can actually bring all of these technologies together, Optimus may no longer be just another humanoid robot. It could become one of the most important physical AI platforms ever created, combining advanced vision, efficient hardware, powerful onboard computing, and Tesla's enormous data engine into a machine designed to operate in the real world. But the biggest question is still how quickly Tesla can turn these ambitious technologies into reliable, mass-produced robots. The technology is evolving rapidly, and the next major Optimus reveal could give us a much clearer picture of just how far Tesla has progressed. What do you think? Could Optimus Gen 3 really become the breakthrough that takes humanoid robots into mass production, or will competitors reach the market first? Let us know your thoughts in the comments below. If you enjoyed this video and want to stay updated on the latest Tesla, Optimus, AI, and robotics developments. Make sure to like this video, subscribe to the channel, and turn on notifications so you don't miss our next update. Thanks for watching, and we'll see you in the next video.